Hello and welcome to another power electronics class. In the previous class, we covered introductions and applications of power electronics and some of their applications, and especially in renewable energy. Today, we will continue with different power electronic interfaces, and we will do a review of semiconductor devices such as diodes, GTOs, MOSFETs, which are metal oxide transistors, IGBTs, and switching characteristics and power losses. And also, if we have time, we would continue with the design of power poles. Our main focus today would be on the electronics interface and switching, using, as I mentioned, the semiconductor devices. And I'll give you some examples. Why do we even need switching? As you know, we have different ways to change the DC voltage, to reduce the DC voltage. And I would compare the efficiency of different methods with switching, and so we can understand which one has the highest efficiency to build a DC to DC converter, for example. So for the power electronic interfaces, imagine that we have a utility power company providing the power, and it's usually like 95% of the time power electronics are used for this. You have an AC voltage input, but your load is either DC or it's an AC load, but with a different voltage or frequency or current. Therefore, we need a power electronic interface to convert that AC utility AC, let's say it's 120 volt, 60 hertz AC, to a DC voltage, to be able to, let's say it's a 5 volt DC, 5 volt 1 amp DC that we want to charge our phone with, or a 12 volts 2 amps for charging your laptop, or a you want to, it's the same voltage but it's a different frequency because you want to control the speed of an AC synchronous motor. So different type of loads. We have adjustable DC load, which are used in power supplies, DC chargers, electric vehicles, etc. We have adjustable AC load for motors, AC LEDs, etc. And we have high frequency AC loads, those who are used in induction heating. If you have these electric coffee makers, or some compact fluorescent lamps. Usually they have very high frequency. We use the eddy current, and the induction heating is actually very it's one of the most efficient systems out there because it converts like 95% of energy to heat. Good. This is a classifying structure in power electronics. We have 3 different type of link systems. We have a voltage link system. We have current link systems, and we have a matrix converters or direct link systems as well. So what is the difference between these 2 different types of links? A voltage link system is a parallel connected system. We usually have 2 converters, and we have a parallel capacitor to form the DC link. It's commonly used in power systems from watts to megawatts, and it's a constant voltage supply. Now, my first question is, why do we need to connect them in parallel? Because when you connect 2 elements in parallel, they would share the same voltage. You want to convert the voltage. You want to transfer that voltage. One example for this could be For example, if you have a utility system that creates a sinusoid voltage, and the converter number one is simply a bridge rectifier, for example, or a rectifier, a half wave or bridge or whatever. And that creates a pulsating AC like this. Now, the rule of this capacitor is to store energy and to be able to smooth the signal. So when the signal passes the capacitor, I'm going to draw it with black. It's going to smooth out the ripple. So you're going to have something that looks like this. And finally, converter number two could be a buck boost converter. So what it could do, it could increase the voltage or decrease the voltage. So imagine this is 5 volts. I'm sorry, let's make it 120 volts. 5 volts is too low for this. And then this is a buck converter, and I'll explain a buck converter, and it's a filter, and it reduces that to 5 volt DC. Okay. So the capacitor here, what it does, it acts like filter, and it actually separates these two converters as well, smooths out the signal. On the right, you see an example of a battery connected to or a source connected to a switch. And what it does, it's when the system is connected to the capacitor, it starts charging the capacitor. You can see that it's charging. And when you connect the capacitor to an LED, the charge goes from the capacitor to the LED and turns on the LED. So the LED is basically the load here. It could be a light, it could be a motor, it could be anything. So you may ask, why do we even need this? Why wouldn't we directly connect that source to our LED? So imagine that this is a PV panel, okay? And for a PV panel, the voltage is fluctuating, and this LED works on 5 volt constant. Okay, so what we're gonna do, we're gonna use that capacitor as a buffer, as a reservoir, charge it, and then using that charge to turn on the LED. Or instead of a PV panel, imagine it's just an AC. And an AC cannot turn on an LED, so you give it to you charge a capacitor, the capacitor smooths out the signal, and you give it to the LED.
So that switch is going back and forth.
Yes, but the frequency is up to us. You can create, instead of one, you can have 2, 3, multiple capacitors to make it more smoother signal, or a much bigger capacitor. These are different type of voltage link systems, and as I mentioned, it could be AC to DC, like what I told you, or DC to DC. The AC to DC was just one example. So the first one that you see here is an AC to DC link. This is exactly what you see in your laptop charger or your phone charger. You have an AC to DC, then there's a DC link, and then we have a DC to DC. So the AC to DC is technically a rectifier. The DC link, again, smooths out the voltage, and you have a DC to DC converter that regulates the voltage. It could be a voltage regulator, it could be a buck converter, and I'll explain about all of that. So at the end, you would have a solid DC with derived voltage. And then we have the AC to AC. So an AC to AC, which are used in wind turbines, I gave you an example of that, or inverters. An AC to DC is first used to rectify, as a rectifier, to convert AC to DC. Then the DC link is used to smooth out the signal. Then there's another DC to AC converter at the end. And the DC to AC is technically a inverter. A sine, here it's a sine wave inverter. Then we have the AC to DC again, and the load here could be a resistive load or energy source. This is the AC DC or DC AC power converters with a DC link. For each of these, we have different applications. So for the first one, AC to DC, can you give me some example of why we need an AC to DC? Again, this first does this, and then we have a signal that looks like this. And finally, this, if it's on 120 volt, for example, goes down to 5 volts. What is this type of link, voltage link used? This is used for anything that you need to charge a battery, like a power supply on your computer, or if you need a DC on your laptop, on your phone, and so on. Where do we need an AC to AC link? When we want to have control over the frequency. So here we have a constant frequency, let's say 60 hertz, and we can change that frequency to say 600 hertz or 6 kilohertz. So communication systems, inductive heating, fluorescent lights, any AC motor that you want to control its speed is using this AC to AC link. Usually the voltage is not changed, or it's like it alternates a little bit, but the thing that it changes is the frequency. We want to have control over frequency. Okay, if we want to change the voltage at the end, we will simply add a transformer or at the beginning, and we can regulate. And an auto transformer, I'll explain later what that is. You can adjust the voltage as well, but the frequency is controlled with the switching cycle, what we call, and that's through the control system. And finally, we have the AC to DC and DC to AC, and these are used again for different, for example, battery storage systems, and to be able to control some power loads, especially resistive loads and energy sources as well. So group one, adjustable DC or low frequency AC. We have the DC and AC motors. We have the UPS, which are the power storage systems. I'll explain more about them. And then we have the DC power suppliers. And the group two, which are high frequency ACs, which are compact fluorescent lamps, induction heating, and also AC motors. Like the one that you see in a Tesla, those actually use the DC to AC. You have a power bank, the battery system. Some of them are 400 volt architecture, some are 800. I think the Teslas are 250 or 200, and that battery like a 60, 70 kilowatt hour. But the motor is an AC motor, so you have to have a DC to AC link to convert that DC voltage to AC. And you need to have control of the frequency to control the speed of the vehicle. And the controller here, you can see the controller in the middle controls the frequency or the voltage in the output. So you can have a controller to control the frequency of the output or the voltage in the output. So the second type of link system is the current link system. The current link system, there's a difference between the current. The main difference, can you spot the difference between the voltage link and the current link? How were the source and the load connected in a voltage link system? Were they connected in parallel or series? They were connected in parallel. Yes. So when you want to have a voltage link, you need to connect them in parallel because you want them to share this voltage. How are the current link systems connected? They are connected in series because we want to convert the current. Usually we have two converters. They are connected, as mentioned, in series. So we have series inductors and to form a current link. One thing that you may remember from electronics is that capacitors are very good at storing voltage. Inductors are very good at storing current. Okay, so whenever you need to regulate or filter a current, you would need an inductor. For voltage, you need a capacitor or battery. So in the previous one, we saw that the capacitor acted like a filter and between the input and output. In the current system, we have the inductor. So a series inductor to form a current link to link both. They are commonly used in a high power system. They're used for constant current supply. And we have an example here that how we do that. Yeah, this is an example of an AC to AC link. The voltage link system is mainly used in most systems. The current link system is, I would say I haven't seen a lot of applications, mainly used for high power AC. They use them a lot, but in everyday electronics, you mainly see the voltage link system. And then we have a matrix converter or the direct link system. They are using AC to AC converters. They have reduced number of components, a low complexity modulation scheme, and they have low realization effort and high efficiency. And we have different type of direct link systems as well. I have added this pictures so you can see. This is an AC DMC and an AC which connects to an AC microgrid. This is one type that we want to connect an AC system to a DC microgrid as another system. So AC microgrid, DC microgrid. This is another AC to DC DMC, so directly converts AC to DC. And then we are connected to a DC microgrid. E is a hybrid DMC connected to a DC microgrid. And also we have connection to an AC microgrid as well. That's the reason we call it hybrid. This is exactly what happens in a if you have a community that has solar panels and a huge battery storage system, and at the same time you want to be connected to the grid, this is the one that you go. So you have the PV panels connected, you have the battery connected, and finally you have the AC microgrid that you have as well. And I'm sorry, you have the AC microgrid that you have. I forgot to show you the AC grid. And this is the AC grid, which is the utility grid that you're connected to. The next one is the AC DMC connected to an AC microgrid. So this is your microgrid that your home and everything runs on. This is the grid the community is running on. And then you have an AC to AC DMC, and which is the direct link that we have, direct link with the matrix converter. And then we have a reduced hybrid system, which again, we have the DC microgrid, AC microgrid, and the grid itself. So one thing to keep in mind is you may think, why do we need a DC microgrid? Okay. Sometimes when you want to run, for example, let's say a small home, a tiny home, a cabin, or an RV, you don't actually need to convert to AC. Okay. In a tiny home, you can build the appliances in a way that everything works on a DC voltage. I would say like 60-70% of all the devices that you use at your home, like lighting, the LEDs, your phones, your laptops, all of them run on DC. The only things that run on AC are your large appliances, such as the HVAC, the refrigerator, your washer dryer, and so on. So if you have a PV panel, an off-grid system, you usually have a DC source. And a problem with when you have an off-grid system is the conversion from DC to AC. And this is the most expensive part. Okay. Imagine a PV panel would be 5K for a 20 kilowatt hour system. The inverter itself is going to be another 4 or 5K. Okay. So one thing that we can do to make the system cheaper is just run everything on DC. So already the lights, chargers, everything, all the electronic things, your TV, everything could run on DC. Also, there are appliances that run on DC as well, such as HVAC. You have the, inverter DC HVACs right now. Refrigerators. We have refrigerators that run on DC. The only big problem may be your washer dryer. Washer isn't a big deal. It doesn't consume a lot of power. Dryer is like 4 or 5 kilowatts. And if you have a car, RV or a tiny home, usually they don't have a dryer. You just dry it on the sun, natural drying. So what we can do, we can get rid of the inverter, which is like in this case like 4K, and have a DC system, a DC microgrid. So all the outlets in the RV or in your tiny home, and I've done that. I actually was installing solar panels for a few years after I graduated from my undergrad. As a side hustle, I was doing PV panels. Back then, PV was just brand new, and it was a start of the boom of solar systems. And batteries were very expensive. Inverters were much more expensive. So what I did is just completely got rid of the battery and inverter and connect everything to the outlets. If someone wanted a battery, I would give them a battery so they can run it. But most, cabins that some people use for their vacation, you just need some lightings that with a small battery, you can just provide the lightings. And if you don't want to run your washer dryer at night, for example, if you're in a mountain in Colorado and you want to have an off-grid, cabin, just a few solar panels and 2 car batteries would run you for a couple of days if you just want to run lighting, So one way is to just convert everything to DC and run all the wires as a DC. But you have to be a little careful with the DC when you run them because the direction of the positive, negative, it's not like AC that you can plug your outlet anyway. So sometimes there are special, outlets for those. But if you want to just run your lights, all the lights that you see in these rooms, LEDs, they usually run on 5 or 12 volts. So you can run an entire RV with a 12-volt system or a 24-volt system. And the other benefit of the system is the loss in the system is almost none, because you don't want to convert AC to DC and then back, or DC to AC and back to DC. Because that's what technically these lights and these chargers do. And you have like 40-50% loss in the system. You're going to directly give a 5-volt, like a USB outlet around the house. And then we have voltage link systems with a switching power pole. This is the basic building block of the DC to DC converters, buck and boost converters. We have a voltage port, and you can see that it's connected in parallel with a capacitor. And then we have our voltage link, which is here, the capacitor, and it's in parallel. And then we have our current port, which is inductor and it's connected in series. And then we have a bipositional switching as well. Now that we learned about voltage link systems, we want to go through some examples of why we do even use these voltage link systems and these switches, and what are the benefits of using these switches. So let's have a discussion topic, discussion on the need for switching in power electronics and power electronic converters. We will give some examples of efficiency, comparison between them, ideal switch characteristics, comparison to practical switching, power loss and practical switching, and several examples on switch loss calculation, conduction, and switching components of loss, and I will give you some examples of those as well. Let me erase this. Yeah, so it's gonna confuse you. I'll get back to this. So why do we need switching? Why do we use semiconductor devices as switching? Because first, it allows better output control. We can have higher frequency response. Allows for improved efficiency. Ideal situation is 100%, and I'll give you some examples. What are the effects of poor efficiency? We have energy costs, design complication, because when you have a lot of loss, you are gonna generate a lot of heat, and therefore the parts should be further apart. You need a bigger board, you need heat sinks, you need a cooling fan, liquid cooling or air cooling. It's gonna make it much more complicated. We have reduced reliability because we generate more heat. The board is gonna last shorter than, it's not gonna last as long as a system with with higher efficiency and lower loss. And we have more component design like the heat transfer and the protections because we generate more heat. Now, let's do some examples of theoretical efficiency examples. We'll do an example to understand why switching is the most energy efficient choice. We will consider the design of a DC to DC converter as shown above. The design requires a 24 volt step down to 12 volt across a 6 ohm resistive load. Let's investigate 3 possible options. So before I start, again, the input is a 24 volt DC and the output is 12 volt DC. So it's a DC to DC converter, but we want to change the voltage. We want to step down the voltage. We want to cut the voltage in half. Based on your knowledge, what is the simplest way that I can convert and step down a 24 volt DC to a 12 volt DC? So imagine if someone comes to you and says, oh, I have a 24 volt battery and I want to turn on this LED or this load, and this LED or this load is 12 volts. How can I connect these two together so I won't burn the LED? Resistors, great. Now the resistors that I want to connect to them, what should the resistors be? I can use a potentiometer, or I can use a voltage divider. Yes. So let's do it with a voltage divider and a potentiometer. I'm actually just want to erase this part. So this is using a simple voltage divider. It could do the job. The voltage divider, as you remember, this is the equation. I'm just going to keep the equation. V out in this situation, which is the voltage of the load resistor, is equal to RL over RL plus R times Vn. Now, what is the load resistor here? We don't know. Imagine that it's, let's say, 6 ohms, for example. And we can calculate it actually. V out, the output voltage, we want it to be at 12 volts. So 12 would be equal to RL over RL plus R, which is 6 ohms, times the input voltage, which is 24. So 24 RL is equal to 12 RL plus 72. So 12 RL is going to be equal to 72, and RL would be equal to 6 ohms, okay, in this particular case. Now let's find the power for the load. What is power for the load? Power equation is equal to VI. Am I correct? Or instead of I can use the Ohm's law. I is equal to what? V over R. Am I correct? So P in the load, the power of the load, is going to be equal to V times V over R, which is V squared over R. You already know this. This is just a reminder. Am I correct? So if I want to find the power in the load, power in RL, it's going to be 12 squared over its R, which is 6. What is my output power going to be? What is the output power here? That is 72 watts. Can you calculate this, please, for me? Make sure. 12 times 12 is 144 divided by 6. Is that correct? $24. Thank you. Yes. 24. It's 144 over 6 is 24. Yes, thank you. So 24 watts. Now, what is the input power? The input power would be the input voltage times the current. Am I correct? And if I want to find this current I is equal to the voltage, the total voltage, over the total resistance, which is R plus RL. So again, it's going to be V squared over the total R, which is R plus RL. So it's going to be again, now this time the voltage that I have is 24 squared over 6 plus 6, which is 12. So it's going to be 24 squared over 12. And what would the power be? I think 48. Am I correct? So it's going to be 48 watts. So the power that is produced, the source power is 48. And the output power that we get is 24. And this is an ideal situation, meaning there's no loss in the wires, resistors, anything. And in the best case scenario, what is the efficiency? It's around 50%. So 50% of the power is lost in the system, in the resistor, specifically it's in resistor R. So imagine if this was a 2 kilowatt system, it's going to immediately melt R. Okay, you need a huge heatsink, fan, it's not going to even work, okay? Believe me, I tried it, it didn't work. And it's trying to just immediately melt down the resistor and make it so hot. So this is first case scenario. What is our other options? What else can I use? What other elements can I use instead of a voltage divider or a potentiometer? And potentiometer is technically the same. Potentiometer is actually, you're dividing the resistors between them. The next option that we can use is a Zener diode, a voltage regulator. So a Zener diode, as you remember, uses the reverse breakdown region. We have the Zener. And as you remember from electronics in the lab, we did a lab on Zener diodes. And in that lab, we increased the input voltage from 5 to 10, 12 volts. And the output voltage was hovering around like 6 volts if we had a 6 volt. So Zener diodes are very good for low voltage if you want to have a fixed output voltage. So when you need some control or regulation, we can use Zener diodes or Zener regulators. A Zener regulator will allow for load variation. So if the load goes up and down, or even the source goes up, you would have minimal changes in the voltage. If you assume a 12 volts Zener voltage, VZ, and IZ at 12 volt is 0.2 amps. The R drop is 5.5 ohms. Then the input power is going to be P out plus PR drop plus P Zener, which is 24 in this case, plus 26.2 watts plus 2.4 watts, which is 52.6 watts. And the output is again 24 watts. So the efficiency here, the input to output at its best is going to be 46%. So you can see that Zener diode is also not good at all, hovering around 50–40%. But usually we don't want to, divide the power in half. We just want to, if we have an input of 9 volts, we want the output to be around 8 volts or 6 volts. So the efficiency could technically be higher, but again, we have this limitation of generating a lot of heat and a low efficiency. What is our other option? Another option that we can use is, do you remember what other options we had in electronics? How did we regulate the voltage in an output of a rectifier, bridge rectifier? Do you recall what we did in a bridge rectifier in the lab specifically? We had a transformer, then we had the bridge rectifier. After that, we had a capacitor, and the final piece was a voltage regulator. You remember the IC that had a aluminum, piece attached to it, the 7805, 7804, or something like that. So it was an IC that looked like this. You had a heat sink, and for example, 7805. And if it starts with the 8, it's a positive voltage regulator, and 7805 is a positive 5 volt, for example. Voltage regulator is technically, you have a transistor with a controller. How many of you had electronics lab with me? Just you? I'm sorry? Yeah, you didn't have it with me, no? Okay, so in the lab we did a part which, and this was your final project if you recall, that we built a rectifier, and in those rectifiers what we use is a voltage regulator. A voltage regulator is an element built of a couple transistors, and it regulates the output voltage. So no, regardless of the input voltage, you're gonna have a fixed voltage in the output. Obviously, you have a range of inputs. You can't give it 200 volts in the input and expect to produce 5 volts. It's gonna immediately melt. And the reason that a voltage regulator has this heat sink at the part end is again because the efficiency is around 50% or so. You're gonna lose 50% of the power. Therefore, um, it's going to generate a lot of heat. So another type is called a line regulator. Let's see if I can move this a little bit so you can see the title. We have the drop resistor inefficient means, and the voltage regulator works in the saturation mode. As you remember, we have the cutoff region, the saturation region, and the active region. The active region was the region that an amplifier works in, and then the cutoff and the switching, we have the saturation region, which the switching occurs, and the active region is what we see most of these transistors work in. If we want to have a switching system, we operate it in these two regions, the cutoff and the turn on and off system. We have direct source connection in these systems usually. We try linear regulator similar to implementation of 7805 or LM317. We regulate a VCE of 12 volts, so V out would be 6 volts and IL would be 2 amps. If we want to find the PN is equal to P out plus PN, which is the transistors, the NPN transistor, and the loss, which gives us total of, and the loss is 2 watts, gives us 50 watts almost, and the input is half of that, and the output, which gives us the best efficiency possible in this situation is again 50%. So we lose half the power. So voltage regulator, Zener diode, voltage divider, none of them are the solutions. So what is the next solution that we may have? Let's first solve an exercise. I'll give you a few minutes to think on this. We consider the Zener diode, Zener regulator shown in this figure. By assuming that minimum Zener current required to keep the operating in the breakdown region is 0.1 amps, as shown. Determine the range of RL, so the output voltage will be regulated at 12 volts. So I'll give you a few minutes to think on this, and then I would solve it. Do I need more time? Okay. So the current coming into this node, IR, splits into two currents. One goes through the Zener diode, so IR would be IL, which is the load current, plus IZ. Therefore, IL would be equal to IR minus IZ. Now, to find the minimal value of RL would be equal to V out over the IL maximum. Now, what is the IL maximum here? So for Zener diode, IZ was 0.1 amps. And IR, point, sorry, 0.2 amps. If it's, yeah, that's a maximum of that. And IR is 2.2 amps. So therefore, RL min would be equal to, I think there's a small, yeah, the breakdown region. This is the IZ, so it's 0.1. The breakdown region current is 0.1. So V out would be equal to, I was looking for it. So V out is, how much is it? 12 volts. So it's going to be 12 over, and IL would be IR, which is 2.2 minus 0.1, gives us 2.1 amps. Over 2.1 amps gives us, can someone calculate this, I think? Around, no, it should be less than 6. 5.7. Oh yeah, thank you. So 5.7 amps. Perfect, thank you. And this is the minimum that RL could be. What is the maximum that RL could be? RL max could be up to infinite. You can just open circuit it and be up to infinite. And you can see that it's right in the range. Let's see what. So note that for regulated output voltage at V out over 12 volt and design value of R.5.45, the input current is fixed at 2.2 amps. Now varying RL will cause IL and IZ to vary according to the following equation. IL would be IR minus IZ using Ohm's law, the Kirchhoff's current law. Or IZ min is equal to 0.1 amps and the fixed IR 2.2 amps, assuming VO is regulated as 12 volts. Then the maximum value for IL max would be 2.1 amps, resulting in the minimal load resistance of 5.7 ohms, and RL max obviously could go up to infinite because that's the minimum, but we don't have any maximums. Okay, now let's study switching. Why do we want to do switching and solve an example of efficiency of a switching system and compared to normal systems? To better understand this, let me put it this way. So previously, when we wanted to regulate the voltage, imagine we have a water tank, water reservoir, which is full of water. Okay. And we wanted to have a gallon of this water. Okay. So I have a smaller reservoir. I just want 1 gallon. And this is, let's say, 30 gallons, okay? What I did previously is I don't have any control of this switch because I connected. For a voltage divider, what I did is I would simply throw away, I would pick 1 gallon and I would throw away and waste another gallon. And imagine this switch is 2 gallons per minute, okay? So what I did in a voltage divider is I would technically use 1 gallon and throw away 1 gallon. And it's the same in a Zener diode, okay? But when you have a switching tool, instead of having this, imagine you have control over this switch, okay? The valve. Imagine you have control over the valve and you can turn it on and off. And you need to just fill up this 1 gallon. So what you can do, and the ratio of this is 2 gallons per minute, okay? How can I fill this 1 gallon tank if the ratio is 2 gallons per minute? I can turn it on for 30 seconds and turn it off for 30 seconds. So I can fill it in half a minute. So instead of turning on for 1 minute and letting half of it go to waste, throw out, I could just have precise control of it. And the second gallon actually has a limited capacity. So I have to wait that one to drain and then fill it up again. So imagine this has, a small drain coming out that it's 1 gallon per minute, something like that. So when you have precise control over how much water, imagine that you have a tank, you want to fill it in the kitchen and go water your flower pot, your plant, okay? You can do 2 things. You can let the water running, fill out your 1 gallon tank, go water it, and the water is still running and going to waste. Or the other thing you can do is you can fill your tank, shut off the faucet, go water your plant and come back and turn it on again, okay? This requires a control system to be able to have control over the valve. But technically, you're not wasting any water. When you're not wasting any water, your efficiency goes up to 100%. In the previous case, you let the water running, the water is going to waste. And if it's half the time that you're, between going and coming back, you're wasting half of the water, efficiency is going to be 50%. And the higher that gets, it's getting worse. Now, how does it work in an electronic system? So in an electronic system, when we have a switching, we have a voltage source, which we don't have any control of. Usually it could be a battery. And then we have a switch. And the important part is the switch. This is the most important part of this system. And then we have our load. So the switch would turn on, let's say 50% of the time. And it would turn off 50% of the time. So in a minute, imagine it's on for 30 seconds and it's off for 30 seconds. In 1 second, it's on for half a second, off for half a second. And at the end, what we do is we calculate the total energy coming in. And we can use a battery or a capacitor to charge it to measure all the energy that is coming in. So what is the average energy if it's turned on half the time and off half the time? The average of 100% and 0% is what? 50%. And how do we measure average? We can measure the total area under this curve, okay? So the total area would be this area, am I correct? Plus the area under this, which is technically 0. So I can have an integral. I can measure the average using the integral. It's going to be 1 over t, which is our period. We want to measure it in t time. And it's between 0 and td, Vn ddt. So it's going to be Vn ddt because it's a square. So it's going to be Vn times ddt. And as you can see here, dt is, for example, here it's half of t. So in this case, particular case, V average would be around here, which is 50% of Vn. So depending on the time, I can change this time from 50%, let's say, to 90% and 10%. If I change it to 90% and 10%, then V average would be 90% of Vn. Or in other words, it's going to be 0.9 Vn. Or it could be 10%, which is going to be 0.1 of Vn. So instead of the voltage regulator, when we use the transistor in active mode, we use as a switch, we turn it on and off, and therefore we would have zero waste. Because when the switch is off, imagine if this is a battery, we're not consuming any power from the battery. So P out when it's off, it's equal to 0. P out or PS when it's on, it's equal to its maximum. So in the time that it switches on, we only are consuming power. When it's off, we're consuming 0 power. And we can use a low pass filter to extract a DC like a capacitor. And in this case, we're gonna have an efficiency of 100%. Again, because we are just using the power when we need it, and we're cutting off the power when we don't need that. Why do we use a low pass filter? Do you remember the different types of filters we spoke about in LIC? We have active and passive filter. Active filters are using op amps. Passive filters use passive elements. We had low pass filter and high pass filter. Which one of them looked like this? Out, in, and one of them looked like this. Which one is high pass filter? Which one is low pass filter? And why do we use low pass filter for this? So we have different type of filters here. Which one is low pass filter? Which one is high pass filter? Let me put it this way. What does a low pass filter mean? Let's put it this way. The frequency response for a low pass filter looked like this. It will cut off the higher frequencies. So this is called a stop band. And it will pass the lower frequencies. What is the frequency of a DC signal? What? Thank you, 0. So a DC signal has a frequency of 0 hertz. So we need a low pass filter to be able to pass a DC signal. Okay? That's the reason when we want to convert a DC, we need a low pass filter. And we want to cut off all the higher frequencies. Now, which one of these two do you think would pass a low frequency or a DC, and which one would block a DC? Number 1 or number 2? Which one is a low pass filter? Louder, please. Perfect. Thank you so much. Number 1. So if we connect a capacitor directly to a DC voltage source, what happens is initially the capacitor is fully charged with the battery. And when it's charged, what happens to the capacitor? It becomes an open circuit and it blocks the flow, the current. So it will block lower frequency. So this is a low pass filter and this is a high pass filter. Okay. because it's gonna block the lower frequency, and when it gets higher, I always show this. This is not accurate, but it gives you a good visualization of how a capacitor works and how you can memorize it. So always imagine this. If you have a capacitor, okay, with a different color. If you have a capacitor, if you have a DC coming in, what happens to the DC signal? It's gonna get blocked. What happens if I have an AC signal? It's gonna pass through. Okay, so this is a good way. Let me do it with a different color. So this is a good way that you can memorize. If you have an AC, it's gonna go through the signal. If you have a DC, it's gonna be blocked with the signal. Okay, this is not accurate. It's just a, visualization, but it's a good way to memorize this. Okay, so we use a low pass filter because we want to only pass the DC signal and we want to block the AC signal. Okay, I think it's enough for today. Thank you so much, and I would see you next week. And if you have any questions, just please let me know and send an email or stop by my office.